single photon of light departing from Earth requires more than 4 years to reach even the nearest star beyond our Sun. At that velocity, which represents the absolute speed limit of our universe, traversing our galaxy would consume 100,000 years. Humanity finds itself imprisoned within a cosmic cage, confined by barriers constructed from the fundamental laws of physics themselves. But what if those seemingly unbreakable barriers could be circumvented? Scientists have discovered a revolutionary method that could potentially propel spacecraft at velocities 10 times faster than light itself, transforming century-spanning voyages into journeys measurable in mere weeks. You're about to discover warp bubbles materializing in actual laboratories, gravitational wave patterns that might reveal alien technology, and energy requirements plummeting from utterly impossible to merely extraordinarily challenging. If you're ready to explore this breakthrough that could redefine reality itself, hit that like button and subscribe, because we're about to examine how humanity might finally break free from its cosmic prison. Our fastest spacecraft ever constructed, the Parker Solar Probe, tears through the void at speeds exceeding 190,000 miles per hour. That sounds impressively rapid until you perform the mathematics and realize it would still require 70,000 years to reach Proxima Centauri, our nearest stellar neighbor. That journey would commence during Earth's last ice age and conclude in humanity's distant future. We remain trapped in a velocity prison from which conventional rockets offer no escape. Light itself propagates at 670 million miles per hour, and even that cosmic speed limit demands 4.5 years to bridge the gulf separating us from Proxima Centauri. Our Milky Way galaxy measures 100,000 light-years from edge to edge. Calculate the transit time and crossing it becomes an odyssey, spanning hundreds of millennia. Every star you observe twinkling in the night sky represents a destination that current propulsion technology renders completely unreachable within any human lifetime, or even within the span of human civilization as we know it. The Voyager probes, launched in 1977, have now travelled barely 14 billion miles from their starting point. They've been journeying through space for nearly 5 decades of continuous flight. Yet despite this epic voyage, they haven't even completely escaped our solar system's gravitational dominion. The stars remain impossibly, frustratingly distant. We are cosmic infants attempting to crawl when we desperately need to sprint across interstellar distances. Here's the brutal, unforgiving truth that keeps astronomers awake at night. Space isn't simply big in a way we can comprehend. It actively mocks every human ambition to explore beyond our immediate neighbourhood. The distances separating stars are so incomprehensibly vast that even travelling at 99% of light speed would transform interstellar missions into generational commitments spanning centuries. Your great-great-great-grandchildren might finally glimpse the destination you originally aimed for, assuming your descendants maintained the mission across all those generations. Every propulsion system humanity has ever constructed operates according to the same fundamental principle. You throw mass out the back of your spacecraft to generate forward thrust. Chemical rockets combust fuel at high temperatures. Ion drives accelerate electrified particles to extreme velocities. Nuclear thermal engines superheat gas and expel it through nozzles. All of them obey the classical physics that Newton described centuries ago, and all of them crawl pathetically compared to the cosmic highway we need to traverse. Scientists have a name for this fundamental limitation. They call it the tyranny of the rocket equation, and it's an absolutely merciless constraint. The more fuel you load onto your spacecraft, the heavier your ship becomes. The heavier your ship, the more fuel you need to accelerate it. The calculation spirals into a nightmare where your fuel tanks must grow larger than the entire cities just to achieve even a tiny fraction of light speed. Adding more thrust, capacity only adds more weight in engines and structure. It's a problem with no conventional solution. We've accomplished remarkable feats. We've dispatched robotic explorers to Mars, landed sophisticated rovers on distant moons, and photographed galaxies at the edge of our observable universe. Yet we remain fundamentally trapped in our own backyard, staring at fences we cannot climb using any technology currently available. the nearest potentially habitable exoplanet sits 4 light-years away. With current technology, reaching it would require 25,000 years of continuous powered flight. Something fundamental must change about how we approach the problem of interstellar travel. The cosmos teems with billions of potentially habitable worlds according to our telescopes, yet we can barely reach the closest rocky bodies in our own solar neighbourhood. What keeps us chained to this painfully slow reality? The answer lies in equations written over a century ago by one man whose genius simultaneously illuminated the universe and imprisoned humanity within speed limits we cannot break. Albert Einstein published his theory of special relativity in 1905, and with those elegant equations, he constructed an invisible prison around all of humanity's future ambitions. His mathematics revealed something profoundly shocking about the structure of reality. Nothing possessing mass can reach or exceed the speed of light, ever, under any circumstances. The universe itself enforces this rule through the fundamental fabric of space and time. The reason sounds deceptively simple when first explained, yet its implications prove devastating for interstellar travel. As objects accelerate closer and closer to light speed, they gain mass, not just a trivial amount that barely matters. The faster you travel, the heavier you become, and this increase follows an exponential curve. A spacecraft approaching light speed would eventually weigh more than entire galaxies. Moving it even 1 mile per hour faster would require adding energy equivalent to stars. This creates a cosmic catch-22 from which no escape exists. You need energy to accelerate mass through space, but accelerating increases that mass, which requires even more energy, which increases mass further. The cycle spirals toward infinity precisely at the moment you would cross the light speed threshold. The universe essentially tells you that you can approach this limit asymptotically, getting closer and closer, but you can never actually touch it, let alone exceed it. Einstein called this a universal speed limit, and for over 100 years his mathematics has held firm against every experimental challenge and theoretical attack. Particle accelerators smash atoms together at 99.99% of light speed, and those experiments confirm his predictions with terrifying precision. Objects really do gain relativistic mass. Time really does slow down for rapidly moving particles. The rules appear absolute and unbreakable. Scientists have attempted everything imaginable to find loopholes in Einstein's equations. They've experimented with exotic propulsion concepts. They've calculated intricate trajectories using gravitational assists from multiple planets. They've proposed generation ships where entire civilizations would be born, live out their lives and die during voyages spanning centuries. None of these approaches changes the fundamental problem. Einstein's equations lock the door to faster-than-light travel and conventional. Physics cannot locate the key that might open it. Physicists describe these laws as inviolable for good reason. Break them, and you don't just violate some arbitrary speed limit. You break causality itself. The principle that causes must precede their effects. You create paradoxes where effects could happen before their causes, where information could travel backward through time, where the logical structure holding reality together would tear apart. The universe would apparently rather collapse into chaos than permit something with mass to exceed light speed. Time dilation makes everything worse for any hypothetical travelers. Even if you somehow reach 99% of light speed through conventional means, time would flow radically differently for you compared to everyone remaining on Earth. A journey feeling like 10 years to you subjectively might span many decades or even centuries for everyone back home. You would return to find everyone you knew long dead, their great grandchildren now elderly strangers. The isolation would be complete and irreversible. Length contraction adds another twisted layer to relativistic travel. At extreme velocities, space itself appears to compress in your direction of travel. Distances physically shrink from your reference frame. A trip that should take years might feel like months to you subjectively, while decades pass for outside observers. The universe warps around fast-moving objects in ways that completely defy common sense and everyday intuition. For generations spanning most of the 20th century, physicists accepted this as the final word on the subject. Light speed represents the ultimate speed limit of the universe. Nothing escapes it. Nothing exceeds it. Teaching this became absolutely fundamental to every physics curriculum on Earth. Breaking the light speed barrier seemed as impossible as creating a square circle, making 2 + 2 = 5, or building a perpetual motion machine. The mathematics appeared to forbid it completely. But some scientists refused to accept permanent defeat. They started asking a radically different question that would eventually crack open entirely new possibilities. What if we've been thinking about movement itself all wrong? What if the problem isn't how to move faster through space, but how to move space itself? Accelerating even a modest spacecraft to light speed using conventional propulsion would require more energy than currently exists in every fuel tank, battery, nuclear reactor, and power plant on Earth combined. Then multiply that incomprehensible amount by 1 billion. You would still fall short of what physics demands. The mathematics behind this nightmare scenario are confirmed, tested, and absolutely ironclad. As velocity increases toward light speed, kinetic energy requirements don't simply grow linearly. They explode exponentially toward infinity. A spacecraft weighing just 1 ton would need approximately 9 times 10 to the 16th joules of energy to reach light speed. That equals the total annual energy output of all human civilization, all consumed in mere seconds just to move a vehicle roughly the size of a car. Nuclear fusion, the same thermonuclear process that powers stars, offers our most energy-dense fuel source currently known to physics. Yet even converting the entire mass of a large asteroid into pure energy would barely budge a decent-sized starship to any meaningful fraction of light speed. We're not discussing difficult engineering problems that clever solutions might solve. We're confronting fundamental impossibilities written into the structure of reality. Project Daedalus, designed by theoretical physicists in the 1970s, proposed using advanced fusion rockets to reach 12% of light speed. That sounds modest until you examine the actual design specifications. The spacecraft would consist mostly of fuel tanks the size of skyscrapers, carrying 50,000 tons of deuterium and helium-3 isotopes. The payload compartment actually carrying cargo and potential crew would be tiny by comparison, dwarfed by the enormous fuel reserves, and that massive vessel would still require 2 decades to reach just the outer edges of our neighbouring star systems. The journey to Proxima Centauri would take 35 years, minimum, making it a one-way mission for any human crew. Antimatter engines could theoretically improve this dismal mass ratio. When matter meets antimatter, they mutually annihilate completely, converting 100% of their combined mass directly into pure energy, according to Einstein's famous equation E = mc². This represents the most efficient fuel theoretically possible under known physics. The problem reveals itself immediately when you examine production capabilities. We can only produce antimatter 1 individual particle at a time using absolutely massive particle accelerators. And storing antimatter without it touching normal matter and exploding requires magnetic confinement bottles that themselves consume enormous electrical power. Producing enough antimatter fuel for a single interstellar mission would take thousands of years with current technology and production rates. Some physicists have proposed solar sails, enormous reflective sheets hundreds of meters across that would be pushed by photon pressure from starlight. These require no fuel whatsoever, just immense patience. The acceleration they provide is glacial, measured in tiny fractions of inches per second, compounding gradually over years and decades. Reaching even 10% of light speed would demand decades of continuous acceleration under ideal conditions, and the sail would need to be miles across, impossibly thin to minimize mass, yet somehow strong enough to avoid tearing apart under the forces involved. Every conventional propulsion method hits this same immovable wall. The faster you want to travel, the more fuel you need. The more fuel you carry, the heavier your ship becomes. The heavier your ship, the more energy you need to accelerate it to your target velocity. Engineers call this diminishing returns. Poets might call it cosmic mockery of human ambitions. Chemical rockets tap out at around 5 kilometers per second maximum velocity. Ion drives might eventually reach 20 or 30 kilometers per second. Nuclear thermal engines could potentially hit 50. Even the most wildly optimistic fusion designs cap around 3,000 kilometers per second, which still represents only 1% of light speed. We're throwing pebbles at a mountain and somehow hoping to move it through sheer determination. The energy trap isn't simply about building more powerful engines or discovering more efficient fuel sources. It represents a fundamental barrier written directly into the structure of reality itself. Einstein's equations ensure that reaching light speed with any object possessing mass demands literally infinite energy. Infinite means impossible under any circumstances. No clever engineering, no breakthrough in material science, no amount of determination or funding can change that mathematical fact. Yet the trap only exists if you continue playing by the old rules. What if movement through space isn't what we actually need? What if there's another way entirely? Miguel Alcubierre was a graduate student at the University of Wales, utterly obsessed with Star Trek, when he decided to actually calculate whether warp drive could function within real physics rather than science fiction. In 1994, he published a paper that made professional physicists pause and reread it carefully, because his mathematics weren't just creative speculation. They were technically correct according to general relativity. The Alcubierre drive concept doesn't attempt to accelerate a spacecraft through space at faster than light velocities. That would violate relativity and require infinite energy, as we've established. Instead, his equations describe creating a bubble of warped space-time around the vessel. Space contracts dramatically in front of the craft, while simultaneously expanding behind it, creating a wave of distorted space-time that carries the bubble forward through the universe. The ship inside remains completely stationary relative to the space immediately surrounding it, experiencing absolutely no acceleration forces whatsoever. Think of this like a surfer riding an ocean wave towards shore. The surfer isn't swimming through the water under their own power or creating their own forward speed. They're being carried along by the wave itself, standing relatively still on their surfboard, while the ocean does all the actual work of movement. Alcubierre's elegant equations described a spacecraft riding a wave through space-time in precisely the same manner. The conceptual brilliance emerges from exploiting a subtle loophole in Einstein's equations that had been hiding in plain sight for decades. Relativity clearly states that nothing with mass can move through space faster than light. That rule remains absolute and unbroken in this scenario. But Einstein never said that space itself cannot move faster than light. In fact, cosmologists know with absolute certainty that space expands faster than light at the edges of our observable universe. That superluminal expansion is precisely how the universe grew from an infinitesimally tiny point to its current incomprehensible size in just under 14 billion years. If space already breaks the cosmic speed limit naturally during universe expansion, why couldn't we harness that same property artificially? Alcubierre's equations demonstrated that you could theoretically create regions of negative energy density in front of a spacecraft, causing space to contract there, while simultaneously generating positive energy behind the craft to cause expansion. The bubble containing the ship would be propelled forward by this asymmetric space-time distortion. No conventional thrust needed, no acceleration forces experienced. The ship simply rides the space-time wave like a surfer. His paper sent shockwaves rippling through the theoretical physics community. For the first time in history, someone had described a faster-than-light travel mechanism using accepted general relativity equations rather than speculative science fiction. It wasn't wild speculation about unknown physics. It was peer-reviewed mathematics published in a legitimate physics journal. The method appeared technically legal according to all known laws governing space-time. Other scientists immediately rushed to verify his calculations, expecting to find errors that would invalidate the concept. They discovered the mathematics held up perfectly under scrutiny. Space-time could theoretically be warped in precisely this manner without violating causality or breaking relativity. The energy requirements proved absolutely astronomical, but crucially, they were technically finite rather than infinite. That represented a massive conceptual improvement over conventional propulsion, which demands literally infinite energy to reach light speed. The Alcubierre drive could theoretically reach any velocity you desired: 10 times light speed, 100 times, 1,000 times. The bubble isn't moving through space in any conventional sense, so relativistic effects like time dilation and length contraction simply don't apply. Crew members inside would experience perfectly normal time, flow. They wouldn't age slower than people remaining on Earth. They wouldn't see distances compress or stars blur. Physics inside the bubble remains completely ordinary and comfortable. Alcubierre himself has admitted in interviews that he never expected the concept to actually work mathematically when he started playing with the equations. He was just a physics student having fun with calculations inspired by his favourite science fiction television show. Yet his recreational mathematics accidentally revealed a genuine possibility hidden within the structure of space-time itself. Reality appeared to contain a cheat code embedded in its operating system, waiting for someone to discover it. Of course, actually constructing such a drive presented complications that made the elegant theory look almost trivial by comparison. But the conceptual door had swung open. The impossible suddenly transformed into merely extraordinarily difficult. That represents genuine progress. Space-time isn't empty nothingness between objects. It constitutes an actual physical thing, a fabric that can bend, stretch, twist, and ripple like an elastic sheet. Every massive object creates an indentation in this fabric, similar to bowling balls resting on a stretched sheet. That indentation is precisely what we experience as gravity pulling us toward massive objects. Einstein described this geometric picture over a century ago, and we've confirmed it through countless experiments. GPS satellites must account for time flowing slightly faster in orbit than on Earth's surface, because they sit higher in the gravitational well, farther from Earth's mass. Experiments with atomic clocks on airplanes show the same temporal effect. Black holes warp space-time so severely that nothing can escape their gravity once you cross the event horizon boundary. Light itself gets trapped. The Alcubierre drive takes this established concept and weaponizes it for propulsion. Instead of letting gravity naturally warp space around massive objects, you artificially create a controlled bubble of warped space-time around your spacecraft. The warp contracts space in front of you while expanding it behind you, generating a wave that propels the bubble forward through the universe. Your ship never actually moves through space in the conventional sense. Space moves around the ship, carrying it along. This sounds like semantic wordplay until you realize it completely sidesteps Einstein's speed limit. Relativity restricts movement through space, but places absolutely no limits on how rapidly space itself can move or expand. That distinction matters profoundly, because all those nightmare side effects of near-light speed travel, time dilation, length contraction, infinite energy requirements, all disappear completely when you're not actually moving through space conventionally. Inside the warp bubble, physics operates normally in every respect. You could walk around the ship naturally, drink coffee without it floating away, play cards, and experience time flowing at exactly the same rate as people back on Earth. No twin paradox where you return younger than your siblings who stayed home. No relativistic effects smearing your vision into incomprehensibility. The bubble isolates you completely from the extreme space-time distortions happening at its boundaries. The space-time wave itself could theoretically move at any velocity you choose. Alcubierre's original calculations suggested 10 times the speed of light would be relatively straightforward to achieve. More recent mathematical refinements have proposed speeds reaching 100 or even 1,000 times faster than light. At those extreme velocities, Proxima Centauri becomes a 2-week trip. The entire Milky Way galaxy, 100,000 light-years across, becomes traversable in a single human lifetime. The entire observable universe could theoretically be crossed in a few million years rather than the hundreds of billions it would take at light speed. The warp bubble would appear profoundly strange to any outside observers watching it pass. Light cannot normally escape from regions of highly compressed space in front of the ship, rendering it partially invisible to external detection. The expanding space behind would severely redshift light into radio wavelengths. The bubble might emit exotic radiation as it propagates, creating a visible wake through space-time itself like a boat cutting through water. From inside the bubble, you would perceive space compressed ahead of you, making distant destinations appear deceptively closer than they actually are. Stars would shift in colour as their light gets distorted by the intense warp field gradients. Looking backward, space would appear to stretch away into apparent infinity, though you would still be able to see your starting point, just at dramatically shifted wavelengths. The mathematics describing these optical effects get extremely complex quickly, involving tensor equations and differential geometry, but the core concept remains beautifully simple and elegant. Surf space-time like an ocean wave, letting the universe do all the hard work while you sit comfortably inside a bubble of normal reality riding along. The key lies in creating asymmetric space-time curvature of just the right shape and intensity. That requires manipulating the energy density of empty space itself in ways that initially seemed almost magical. Which brings us directly to the biggest obstacle preventing actual construction of this revolutionary drive. A problem that seemed absolutely insurmountable for decades. Alcubierre's warp drive requires something that probably doesn't exist anywhere in the known universe. Exotic matter with negative mass and negative energy density. This isn't antimatter, which annihilates regular matter in spectacular bursts of gamma radiation and pure energy. This represents something far stranger and more problematic. Matter that repels gravitationally instead of attracting, pushes instead of pulls, and essentially makes gravity work completely backward. Normal matter curves space-time inward, creating the gravitational wells that hold planets in stable orbits and make apples fall from trees toward Earth's center. Exotic matter would curve space-time outward, creating what physicists call a gravitational hill that actively pushes objects away. It represents the polar opposite of everything we understand about how mass and energy behave throughout our universe. Does negative mass actually exist somewhere? We've never observed it directly through any telescope or experiment. No one has ever measured it, artificially created it in laboratories, or found compelling evidence of it occurring naturally anywhere in the cosmos we can observe. It remains entirely theoretical, a mathematical possibility that the equations of general relativity technically permit, but that nature has apparently never bothered to actually manifest in physical reality. The quantity needed makes the situation dramatically worse. Alcubierre's original calculations suggested you would require negative mass equivalent to the total mass energy of Jupiter just to warp space around a relatively small spacecraft. Jupiter weighs approximately 300 times more than Earth. Converting that stupendous amount of normal matter into exotic negative mass, even if somehow possible, would require energy expenditures dwarfing anything humanity could conceivably generate. Critics immediately pounced on this seemingly fatal requirement. Sure, they acknowledged, the mathematical framework is valid and the equations technically work, but demanding materials that don't exist makes the entire concept useless for practical purposes. You might as well design an elaborate perpetual motion machine that runs on unicorn tears. The underlying physics might check out mathematically, but the required ingredients remain pure fantasy. Some researchers desperately tried to find alternatives that might work. Could intense electromagnetic fields create temporary regions of negative energy density in quantum vacuum? Perhaps quantum fluctuations could be precisely manipulated to generate the required exotic effects. Dark energy, the mysterious force causing the universe's expansion to accelerate, exhibits some properties superficially similar to negative pressure. Could we somehow harvest or concentrate dark energy for use in warp drives? These intriguing questions generated decades of theoretical papers and intense debates, but produced no practical experimental answers. creating sustained regions of negative energy density at useful scales appear to fundamentally violate several core principles, including quantum field theory's energy conditions. The universe seems to have built-in safeguards preventing large-scale negative energy concentrations, probably to avoid causality violations and reality-breaking paradoxes. The Casimir effect offered a tiny glimmer of hope in this otherwise hopeless situation. When you place two uncharged metal plates extremely close together in perfect vacuum, quantum fluctuations between them create measurably less energy density than exists in the surrounding space. That technically counts as negative relative energy density compared to normal vacuum. Though the absolute energy value remains positive, the differential effect is real, measurable, and repeatedly confirmed in laboratories worldwide. Could this subtle principle possibly be scaled up dramatically? If you could artificially create and manipulate Casimir-like effects on much larger scales, you might generate the space-time distortions needed for functional warp bubbles without requiring exotic matter at all. The energy would still need to come from somewhere enormous, but at least you would be working with demonstrated physics rather than purely theoretical ghosts. This is precisely where Harold White enters the story, and where everything transforms from pure abstract theory into something approaching actual experimental physics that could eventually be engineered. Dr. Harold White spent years conducting research into advanced propulsion physics at NASA's Johnson Space Center in Houston, Texas. His team operated a small laboratory dedicated to investigating exotic propulsion concepts, precisely the kind of fringe science that makes conventional colleagues raise skeptical eyebrows but occasionally produces revolutionary breakthrough discoveries that transform entire fields. In 2011, White published completely new calculations suggesting the energy requirements for an Alcubierre warp drive might be orders of magnitude lower than originally estimated. His revised mathematics demonstrated that carefully optimizing the shape of the warp bubble could potentially reduce energy needs by factors of millions or even billions. Instead of requiring Jupiter mass amounts of exotic matter, his optimized design might only need several hundred kilograms. Still exotic and unavailable, certainly, but suddenly the concept shifted dramatically from physically impossible under any conceivable circumstances to merely incredibly difficult with current technology. Then in 2021, something completely unexpected occurred. White's team was studying the Casimir effect using specialized equipment designed to measure nanoscale forces between precisely positioned metal plates. They weren't attempting to create warp bubbles or test propulsion concepts. They were investigating whether Casimir forces might prove useful for precision spacecraft attitude control in microgravity. Basic fundamental research, nothing revolutionary or dramatic. During one routine experimental run, their extremely sensitive sensors detected something bizarre and unprecedented, a measurable distortion in spacetime at the nanometer scale. The readings matched theoretical predictions almost perfectly for what a microscopic warp bubble geometry should look like. They had accidentally created the exact space-time curvature that Alcubierre mathematically described, just at scales millions of times smaller than needed for actual propulsion applications. White's team meticulously repeated the experiment dozens of times with careful controls. The effect remained perfectly consistent and clearly measurable across all trials. They weren't observing instrument errors, electromagnetic interference, or quantum noise artifacts. They were detecting genuine, reproducible space-time distortion created by manipulating the Casimir effect between conducting plates. A warp bubble, microscopic but absolutely real, had spontaneously appeared in an Earth laboratory. The implications detonated through the small propulsion physics community like a bomb. Warp drive geometry wasn't merely theoretical mathematics anymore. It could be physically created, precisely measured and carefully studied through experimentation. If you could generate a nanoscale warp bubble in a laboratory, then scaling up dramatically becomes primarily an engineering challenge rather than a fundamental physics impossibility. That represents a profound conceptual shift. Critics immediately and correctly demanded independent verification before accepting such extraordinary claims. Other laboratories needed to reproduce White's results using different equipment before anyone could claim definitive proof of actual warp bubble creation. The instruments required are highly specialized and extremely expensive, so independent confirmation inevitably takes considerable time. Some skeptical physicists suggested alternative explanations for White's measurements. Perhaps electromagnetic interference was creating misleading readings. Perhaps quantum effects were being systematically misinterpreted. Healthy skepticism remains absolutely essential in science. Yet White's team had painstakingly calibrated their instruments, carefully accounted for every known source of potential error, and meticulously documented everything following rigorous scientific protocols. The data appeared solid and reliable. More importantly, the anomalous effect appeared precisely when theory predicted it should emerge and vanished when experimental conditions changed. That kind of correlation strongly suggests real physical phenomena rather than mere measurement artifacts or wishful thinking. NASA quietly but significantly increased funding for White's laboratory. Other government agencies took serious notice of the results. Private aerospace companies started actively hiring propulsion physicists to investigate warp field generation possibilities. The race began, not to immediately build functional warp drives, but to rigorously understand whether scaling up from nano to macro scales might actually be achievable with sufficient resources. The exotic matter problem still loomed enormously large. Even with dramatically reduced energy requirements, you still fundamentally needed regions of negative energy density to create the required asymmetric space-time curvature. White's experiments showed Casimir effects could produce warp-like geometry, but only at absolutely tiny scales using minuscule amounts of energy manipulation. Going from nanometers to meters represented approximately a billion-fold increase in scale and difficulty. An enormous engineering gap remained. Still, the crucial psychological barrier had completely shattered. Warp bubbles existed in physical reality, not merely on theoretical paper or in computer simulations. That single fact changed absolutely everything about how physicists approach the problem. Suddenly, research teams worldwide started retrieving old warp drive papers from archives and looking meticulously for overlooked details. Maybe the solution had been hiding in plain sight all along, waiting for experimental confirmation to make it obvious. The race toward practical warp drive technology had truly begun. Someone somewhere would eventually find the key that unlocks scaled-up versions. The question transformed from whether it's possible to when we'll achieve it, and who gets there first. When Alcubierre first calculated energy requirements for his revolutionary warp drive concept, the numbers were absolutely apocalyptic. You would need to convert the entire mass of Jupiter into pure energy somehow, and concentrate that incomprehensible power into exotic matter exhibiting negative energy density. That equals approximately 2 times 10 to the 30th kilograms, or roughly 1.9 times 10 to the 47th joules of energy. For proper perspective on those incomprehensible numbers, the most powerful nuclear device ever detonated in human history released about 2.1 times 10 to the 17th joules. You would need that massive bomb's energy output multiplied by 1 trillion times over. Those stupefyingly large numbers killed serious practical interest immediately among most researchers. The mathematical framework was undeniably elegant, and the concept appeared legal according to relativity's rules, but requiring more energy than stellar cores made the whole idea seem like an interesting theoretical curiosity with zero practical application potential. But Harold White noticed something subtle in the complex equations. Energy requirements depended heavily on 2 specific factors that Alcubierre had chosen somewhat arbitrarily. The thickness of the warp bubble wall separating normal space from warped space, and the overall geometric shape of the bubble itself. Alcubierre's original model employed relatively thick walls and a simple spherical geometry, primarily because that made the tensor mathematics much cleaner and easier to solve analytically. what if you systematically optimize those parameters using powerful computers? White proposed reshaping the bubble into a toroidal configuration, more like a donut than a simple sphere. He calculated that making the bubble wall oscillate in thickness rather than remaining static could dramatically reduce energy needs through resonance effects. The mathematics became significantly more complex and computer-intensive, but modern supercomputers could easily handle the computational load. When White ran his optimized numerical simulations, the results shocked everyone in the field. Energy requirements dropped from Jupiter mass levels down to something closer to 500 kilograms of exotic matter equivalent. Still enormous by any normal measure, still requiring exotic materials we don't possess, but several orders of magnitude more reasonable than before. That mass equals approximately one small communication satellite. You could theoretically fit the required exotic matter inside a spacecraft, rather than needing planet-sized energy sources. Further mathematical refinements by various research groups continued steadily improving the outlook over subsequent years. Different teams proposed various alternative bubble geometries, elongated ellipsoids, figure-8 configurations, nested concentric shells with carefully calibrated different density gradients. Each optimization incrementally chipped away at energy requirements. Some recent theoretical papers suggest you might ultimately only need several dozen kilograms of negative energy density if you achieve precisely optimal geometry. These dramatic improvements emerge purely through mathematical optimization, systematically finding more efficient methods to warp space-time that achieve identical propulsive effects using substantially less energy input. It mirrors how aeronautical engineers improved rocket efficiency over decades by meticulously refining nozzle shapes, fuel mixture ratios, and combustion chamber geometries. The fundamental physics remained unchanged, but clever optimization extracted dramatically better performance from the same basic principles. The really exciting development came when researchers realized you might not actually need sustained exotic matter at all for propulsion. Some sophisticated models suggest you could potentially use ordinary positive energy to temporarily create fleeting regions of negative energy density through carefully orchestrated quantum effects, maintaining them just long enough to generate thrust pulses, then allowing them to naturally collapse before recreating them. Think of it analogously to internal combustion engines that burn fuel in rapid pulses rather than sustaining continuous combustion. This pulsed warp drive concept could theoretically run on advanced fusion reactors or even antimatter annihilation without requiring permanent exotic matter storage. You would still need exotic quantum effects to occur, but only transiently and in precisely controlled microscopic ways. That fundamentally shifts the challenge from impossible material science to extremely difficult but potentially achievable precision quantum engineering. Could these mathematical optimizations really work in physical reality? The mathematics appears rigorous and sound, confirmed independently by multiple physicists using different analytical approaches. But mathematics only reveals what might be theoretically possible according to known physical laws. Whether reality actually cooperates with these optimized theoretical models remains completely unproven until someone constructs actual working hardware and tests it. Still, dropping energy requirements from Jupiter mass to satellite mass represents absolutely genuine progress toward practicality. It moved warp drives conceptually from completely impossible under any circumstances to merely extraordinarily difficult with current technology. Sometimes that seemingly subtle distinction makes all the difference between permanent fantasy and eventual reality. The timeline to practical applications remains uncertain, but the direction of progress is unmistakably positive. Gravitational waves ripple through space-time whenever massive objects accelerate violently through space. Colliding black holes, merging neutron stars, and supernova explosions all broadcast these ripples, propagating across the cosmos at light speed. We can now detect them using observatories like LIGO and Virgo, which measure space-time distortions smaller than a proton's diameter through incredibly precise laser interferometry. In 2024, a research team at Germany's University of Potsdam published a fascinating paper proposing a clever application. If warp drives artificially warp space-time to achieve propulsion, they should also inevitably generate characteristic gravitational waves as a side effect. The pattern would be distinctive and recognizable, fundamentally different from natural astronomical sources we've catalogued. A moving warp bubble would create highly specific signatures in the gravitational wave spectrum based on its precise geometry, velocity, and acceleration profile. The researchers ran detailed computer simulations calculating exactly what these hypothetical warp drive signatures would look like in gravitational wave detector data streams. They computed the characteristic frequencies, amplitudes, and polarization patterns that different warp drive designs would theoretically produce as they move through space. Then they began systematically examining existing gravitational wave observational archives, searching for potential matches to their calculated signatures. Nothing conclusive turned up in current limited data archives, but gravitational wave astronomy remains remarkably young as scientific disciplines go. LIGO only achieved its first confirmed detection in 2015, barely a decade ago. We've only just begun listening to the universe through this entirely new observational window. Advanced detectors coming online throughout the next decade will prove far more sensitive, capable of detecting much fainter signals and distinguishing increasingly subtle patterns from background noise. If any sufficiently advanced extraterrestrial civilization anywhere within several billion light years has successfully developed functional warp drive technology, we might potentially detect their spacecraft moving through space by observing the gravitational ripples they leave behind in space-time's fabric. Those propagating ripples would expand outward at light speed, creating expanding shells of distorted space-time that eventually wash over Earth like waves reaching distant shores. The implications prove staggering to contemplate. We could potentially discover that faster-than-light travel is genuinely real and achievable, not by inventing it ourselves first, but by detecting alien civilizations already routinely using it. Each detection would provide invaluable clues about how they engineered their warp drives, the energy signatures, the bubble geometries, the propulsion timing methods. It would resemble discovering alien footprints in mud and reverse engineering their footwear from the impressions left behind. Some critics reasonably argue that any civilization technologically advanced enough to construct functional warp drives would probably exercise great care about detection and exposure. Maybe they deliberately shield their gravitational signatures using techniques we haven't imagined. Perhaps they employ modified warp geometries specifically engineered to minimize all detectable emissions. They might carefully avoid traveling through populated galactic regions at warp speed to prevent accidentally revealing themselves to less developed civilizations. But even extremely careful civilizations might occasionally leave detectable traces. A single, unshielded warp jump during an emergency, an unplanned maneuver to avoid collision, or simply primitive early warp drives from their initial development period before they perfected signature reduction. We only need to observe one unambiguous example to conclusively prove the concept works in physical reality. Under actual operating conditions, the search naturally expands well beyond just gravitational waves. Warp bubbles moving at extreme velocities through diffuse interstellar gas and cosmic dust should create distinctive shock waves and radiation signatures at specific wavelengths. High-energy particles being accelerated at intense bubble boundaries might produce characteristic gamma-ray or cosmic ray burst patterns. Optical telescopes could systematically search for the distinctive red and blue shifting of starlight around moving warp fields. No confirmed detections exist yet in our limited data. The universe appears frustratingly quiet on these specific frequencies, at least in the relatively small data volumes we've carefully examined so far. But absence of evidence never constitutes evidence of absence, especially when we've only been listening seriously for a handful of years, using equipment with limited sensitivity and sky coverage. Imagine the profound moment when we detect that first completely unambiguous warp drive signature in our observational data. It would instantly answer two of humanity's most profound questions simultaneously. Are we truly alone in this vast universe? And can faster-than-light travel actually work in physical reality? The discovery would revolutionize physics practically overnight and potentially accelerate our own warp drive research programs by decades or even centuries. We would know with absolute certainty that the universe genuinely permits this technology to exist and function. Until that momentous detection occurs, the systematic search continues expanding. More sensitive detectors come online every year worldwide. Analysis algorithms grow increasingly sophisticated. Data processing techniques improve continuously. If alien warp drives are actually out there somewhere leaving their distinctive signatures permanently imprinted on space-time itself, we will eventually find unmistakable evidence. It's only a matter of time and systematic effort. Faster-than-light travel terrifies some theoretical physicists because it might potentially enable time travel under certain conditions, and time travel creates devastating logical impossibilities that fundamentally threaten the consistency of reality itself. The grandfather paradox illustrates this philosophical nightmare perfectly. If you somehow travel backward through time and prevent your grandfather from ever meeting your grandmother, you logically never get born. But if you were never born, you obviously never travelled back through time, but then your grandfather does meet your grandmother after all, so you do get born, so you do travel back, creating an infinite causal loop with absolutely no consistent resolution possible. Warp drives potentially enable similar paradoxes on cosmic scales according to some interpretations of relativity. If you travel faster than light between two reference frames moving relative to each other at high velocity, certain observers could theoretically conclude you arrived at your destination before you actually departed. The mathematics gets extraordinarily ugly and complex rapidly, involving closed time-like curves and apparent violations of causality. But the disturbing conclusion seems difficult to escape. Faster-than-light movement and time travel appear intimately connected within relativity's framework. Some physicists argue this connection conclusively proves faster-than-light travel must be fundamentally impossible regardless of clever engineering. The universe simply cannot permit causality violations because they create logical contradictions that break reality. If effects can precede their causes, nothing makes coherent sense anymore. You could potentially receive answers before formulating questions, die before being born, prevent events that already happened. Reality would collapse into incoherence. Stephen Hawking proposed what he called the chronology protection conjecture, suggesting unknown physics automatically prevents time travel from occurring even if naive equations appear to permit it mathematically. Whenever someone attempts to create a functional time machine or travel faster than light, quantum effects or other poorly understood mechanisms would inevitably intervene to prevent paradoxes from actually manifesting. The universe fundamentally protects its own logical consistency through mechanisms we don't fully understand yet. Other scientists point out that warp drives might naturally avoid these paradoxes through their specific geometric structure. The space inside the bubble moves faster than light relative to external space, but crucially, nothing ever crosses the light speed barrier locally at any point. Information cannot propagate backward through time via the bubble, because the bubble geometry inherently isolates its interior from problematic external reference frames. Additionally, warp drives require continuous substantial energy input to maintain the intense space-time distortion. That energy must come from somewhere, typically fusion or antimatter reactions happening in real time as the drive operates. You cannot retroactively provide energy to a warp bubble that already collapsed in the past. This temporal directionality built into energy requirements might inherently prevent any backward time travel, even while permitting faster than light velocities. The honest truth remains that we genuinely don't know whether faster than light travel inevitably creates paradoxes because we've never achieved it experimentally. The universe might have subtle protection mechanisms we haven't imagined yet. What remains absolutely certain is that successfully building a working warp drive would immediately illuminate these deep questions. Either paradoxes emerge and we discover new physics explaining how they resolve, or they don't emerge and we learn causality protection is somehow built directly into space-time structure. Either outcome represents a revolutionary discovery that transforms our understanding of reality. NASA's Advanced Propulsion Physics Laboratory operated quietly for years under Harold White's careful direction, tucked away in Building 9 at Johnson Space Center in Houston. The official mission statement sounded deliberately mundane: study exotic propulsion concepts for potential future applications. The unofficial reality involved active, ongoing warp drive research funded through carefully worded budget requests that avoided attracting too much premature attention. White's dedicated team built increasingly specialized equipment to measure nanoscale space-time distortions with unprecedented precision. They systematically experimented with different capacitor, plate configurations, attempting to amplify Casimir effects through geometric resonance. They ran endless computer simulations exploring optimal warp bubble geometries. The research proceeded carefully and methodically, always maintaining plausible scientific cover stories for anyone in administration, asking uncomfortable questions about seemingly impossible goals. Then came the 2021 public announcement about detecting warp bubble signatures in laboratory experiments. Suddenly, the quiet research couldn't remain obscure anymore. Media coverage forced NASA leadership to either publicly disavow the research as fringe speculation or officially acknowledge its scientific legitimacy. They chose a careful middle path, confirming the research program exists while heavily emphasizing its extremely preliminary nature and multi-decade timeline to any potential practical applications. Behind closed doors, however, funding reportedly increased substantially. More physicists with relevant specializations joined the expanding team. Equipment purchase orders grew more ambitious. The laboratory that barely existed officially now operated multiple parallel research tracks simultaneously. Other NASA centers got involved in supporting roles. Glenn Research Center in Ohio contributed propulsion engineering expertise. Jet Propulsion Laboratory in California brought advanced systems engineering capabilities. Ames Research Center provided supercomputer access and sophisticated computational modeling resources. The research network quietly expanded across multiple facilities, each working on different interconnected pieces of the larger puzzle. Government security classification adds murky layers of uncertainty. Some warp drive research almost certainly proceeds behind security clearances, completely invisible to public oversight and academic peer review. If breakthrough discoveries occur within classified programs, we might not learn about them for years or potentially decades. Military applications of faster-than-light travel remain obviously significant enough that defense agencies certainly fund their own parallel research programs outside public view. The Department of Energy probably participates significantly, given the extreme energy requirements fundamentally involved in any warp drive system. Their national laboratories possess deep expertise in plasma physics, advanced fusion reactions, and high-energy particle physics. If exotic matter generation or vacuum energy manipulation proves remotely possible, DOE facilities would be optimally positioned to attempt it. International scientific collaboration remains severely limited by national security concerns. NASA shares some basic fundamental research results with allied space agencies through established channels, but anything approaching practical engineering applications gets immediately locked down behind classification. No nation wants to hand potential adversaries such a massive strategic technological advantage. The first country to achieve working warp drive technology would completely dominate both peaceful space exploration and potentially military operations. This unfortunate reality creates excessive secrecy around research that humanity as a whole might benefit enormously from openly sharing. Scientists at institutions worldwide probably unknowingly duplicate substantial efforts, each group independently struggling with similar fundamental problems that genuine collaborative work could potentially solve much faster. But harsh geopolitical realities prevent open international cooperation on anything with clear military sensitivity. how close is NASA really to a working prototype? Publicly, they maintain that practical warp drives remain far future speculation, possibly achievable in 50 to 100 years with sustained research funding. Privately, some researchers hint that breakthroughs could potentially come much sooner if several critical problems get solved in fairly rapid succession. The gap between those official and unofficial timelines might hide classified progress, or might simply reflect the difference between conservative official estimates and optimistic scientific hope. Elon Musk rarely discusses warp drives in public interviews or presentations, but SpaceX's ambitious long-term plans for Mars, colonization and interplanetary expansion strongly suggest someone within the organization is seriously thinking about revolutionary faster propulsion systems. The company's massive Starship program explicitly aims to establish permanent self-sustaining cities on Mars, but Mars represents merely a stepping stone in Musk's grander vision for humanity's future. He has stated repeatedly in various forums that making humanity a genuinely multiplanetary species ultimately requires reaching other star systems eventually. You cannot build a true spacefaring civilization confined to one solar system. SpaceX employs some of the world's most talented propulsion engineers and theoretical physicists, many recruited from top universities and national laboratories. Their extensive facilities in Hawthorne, California, Boca Chica, Texas, and Cape Canaveral, Florida house cutting-edge laboratories capable of conducting advanced fundamental research. The company's organizational culture actively encourages moonshot thinking and rapid prototype iteration. If any private organization would seriously pursue warp drive research with substantial resources, SpaceX tops the list of likely candidates. Specific technical details remain deliberately scarce and carefully guarded. SpaceX treats proprietary research like classified government information, revealing only what strategically benefits them through carefully managed public relations. But job postings occasionally hint at exotic propulsion studies that go far beyond conventional chemical rockets. Engineers with specialized backgrounds in plasma, physics, quantum field theory, and general relativity get actively recruited for unspecified advanced projects that never get publicly detailed. Equipment purchasing records, when they leak, include highly specialized sensors and high-energy experimental systems with no obvious connection whatsoever to conventional rocket development programs. Persistent rumors circulate about secret test facilities in extremely remote locations, where unusual experiments occur completely away from public scrutiny and media attention. Some former SpaceX employees describe vague research tracks exploring physics well beyond chemical combustion rockets, though strict non-disclosure agreements prevent them from providing specifics. One anonymous source mentioned studying space-time manipulation techniques in passing, but independent verification proved completely impossible. Musk's other companies might contribute synergistically to warp research in unexpected ways. Boring Company expertise in underground construction could potentially build heavily shielded facilities for dangerous high-energy experiments that require isolation. Tesla's advanced battery and power management technology might enable the extraordinarily precise energy control needed for warp field generation and maintenance. Neuralink's groundbreaking work on brain-computer interfaces could theoretically help manage the phenomenally complex calculations required for real-time warp field manipulation and navigation. The combined financial resources available to Musk personally and through his interconnected companies collectively dwarf most government research budgets by substantial margins. SpaceX alone generates billions annually from Starlink satellite launches and lucrative NASA contracts. That massive sustained revenue stream could easily fund highly speculative fundamental physics research if Musk personally decided the potential long-term payoff justified the substantial investment. He has repeatedly demonstrated willingness to bet enormous resources on long-shot technologies that conventional wisdom dismisses as impossible or impractical. Blue Origin, Jeff Bezos's privately funded space company, presumably conducts similar speculative research behind their own veil of secrecy. Bezos clearly shares Musk's expansive long-term vision of dramatically expanded human presence throughout the solar system and beyond. Blue Origin employs exceptionally talented aerospace engineers and physicists with access to substantial financial resources. Their New Glenn rocket and lunar lander programs generate significant revenue, while more speculative blue sky research proceeds quietly in the background away from public view. Other major aerospace corporations like Lockheed Martin, Boeing, and Northrop Grumman maintain advanced concepts divisions that explore exotic propulsion possibilities as part of their long-range strategic planning. These operate with far less publicity than SpaceX's high-profile activities, but likely pursue similar fundamental research directions with substantial budgets. Defense contracting relationships give them privileged access to classified research programs and government funding for highly speculative long-term projects. Silicon Valley billionaires fascinated by space exploration might fund independent research groups outside traditional corporate structures. Yuri Milner's Breakthrough Initiatives already sponsors multiple projects searching for alien life and developing interstellar probe concepts. Breakthrough Starshot explicitly aims to send tiny laser-propelled spacecraft to Alpha Centauri at 20% of light speed within coming decades. These well-funded initiatives demonstrate clear willingness to invest hundreds of millions in revolutionary propulsion concepts that mainstream science considers extremely risky. Private research avoids some stifling government bureaucracy and security classification restrictions, potentially enabling faster iteration cycles and more aggressive risk-taking on unconventional ideas. But it also lacks the deep institutional knowledge, world-class facilities, and extensive collaborative networks that government laboratories provide through decades of accumulated expertise. The ideal situation might involve structured partnerships between public and private sectors, pooling resources and knowledge, but intellectual property concerns and national security classifications severely complicate such collaborative arrangements in practice. What remains abundantly clear is that multiple extremely well-funded organizations beyond NASA are actively pursuing faster-than-light propulsion research with serious intent and substantial budgets. The race has truly begun, though conducted mostly in secrecy behind closed doors. Whoever achieves the first genuine breakthrough will either become incomprehensibly wealthy and powerful, or spark a new era of space exploration that fundamentally transforms humanity's future trajectory. Quite possibly both outcomes simultaneously. Time dilation at velocities approaching light speed creates one of the cruelest aspects of conventional, near-light speed travel using traditional propulsion. Einstein's equations predict that time flows measurably slower for rapidly moving objects compared to stationary observers left behind. The faster you travel, the more dramatically pronounced this effect becomes through relativistic mechanics. At 99% of light speed, time passes approximately 7 times slower for you than for people remaining on Earth. This means a subjective 10-year journey from your perspective equals 70 years passing back home. You return having barely aged to find your friends and family elderly or long dead, your children now older than you, society transformed beyond recognition by decades of change. The isolation proves profound and completely irreversible. You become unstuck in time, living a paradoxical existence where personal and external clocks no longer synchronize in any meaningful way. Warp drives elegantly sidestep this entire horrifying temporal disconnect because the spacecraft inside a warp bubble isn't actually moving through space at relativistic speeds in any conventional sense. Time dilation effects simply don't apply to the bubble's contents. The bubble itself moves through space, but it carries normal, undistorted space-time along with it. Inside, time flows at exactly the same rate as on Earth. You could travel to Proxima Centauri in mere weeks, return home, and find only weeks have passed everywhere. Your relationships remain intact. Your knowledge stays current and relevant. You don't become a temporal refugee displaced from your own era by the cruel mathematics of relativity. This represents one of warp drive's biggest practical advantages beyond simple velocity. you maintain genuine temporal connection with home across interstellar distances. Crew members would experience completely normal time flow throughout the journey, aging naturally at standard rates during transit. No suspended animation needed, no generational planning required, no severe psychological trauma from temporal disconnect. The mission, timeline, gets measured in human lifetimes rather than civilizational epochs spanning centuries. This also makes warp travel economically viable for practical purposes. A private corporation funding an interstellar mining operation needs results within investment horizons measured in decades, not centuries or millennia. Governments planning colonization efforts cannot wait generations for meaningful feedback from distant colonies. Warp drives enable interstellar activity to operate on timescales that actually make sense for human institutions, motivations, and economic planning. The James Webb Space Telescope has revealed a universe far larger and more densely populated than we ever imagined possible. Trillions of galaxies fill observable space, each potentially harboring billions of habitable worlds scattered throughout cosmic time. Yet all of it remains permanently beyond our reach using conventional propulsion, forever bound by light speed limits. Warp drive technology represents humanity's only realistic hope of actually exploring that cosmic abundance within meaningful timeframes that matter to living people. What remains absolutely certain is that serious, well-funded research continues at multiple government facilities, using increasingly sophisticated experimental equipment and theoretical techniques. Warp drives have completely transitioned from pure science fiction fantasy into legitimate government-funded physics research programs. That represents enormous conceptual progress regardless of how far from practical flight applications we currently stand. The technology that seems impossible today becomes tomorrow's routine reality. History demonstrates this pattern repeatedly. Heavier-than-air flight seemed impossible until the Wright brothers achieved it. Splitting the atom was theoretical fantasy until it suddenly wasn't. Computers were room-sized experimental devices that became pocket-sized ubiquitous tools. Warp drives follow the same trajectory from impossible to difficult to eventually routine. Every breakthrough brings renewed optimism and revised timelines. Some researchers privately suggest that a single critical discovery could transform everything practically overnight. If someone discovers how to generate scalable negative energy density reliably, or learns to manipulate dark energy effectively, or finds some completely unexpected space-time manipulation technique, the entire developmental timeline could collapse dramatically. We might go from barely able to measure nanoscale effects to constructing test vehicles within just a few years of intensive focused effort. History repeatedly shows that technological revolutions often happen faster than experts predict once key enabling discoveries finally occur. Powered flight progressed from barely possible to routine within 2 decades. Nuclear energy became practical within 5 years of achieving theoretical understanding. Computers shrank from room-sized to pocket-sized in 30 years. The right breakthrough triggers explosive cascading progress across related fields. The theoretical frameworks already exist in peer-reviewed literature. The mathematical models have been extensively validated. Laboratory experiments have demonstrated warp bubble geometry at small scales. Energy requirements have dropped from impossible to merely extraordinarily challenging through systematic optimization. Multiple well-funded organizations pursue the goal. With serious resources and talented teams, all the foundational pieces are falling into place like a cosmic puzzle, slowly revealing its complete picture. Imagine the moment when the first crewed warp test flight launches from Earth. A small craft carrying a handful of brave volunteers accelerates away from our planet, engages its experimental warp drive, and vanishes from conventional detection. Hours or days later, it reappears light years distant, its crew reporting successful faster than light transit. That single achievement would rank among humanity's greatest accomplishments, standing alongside controlled fire, agriculture, and leaving Earth's surface entirely. The psychological impact would reshape how billions of people think about humanity's place in the cosmos and our species' ultimate destiny among the stars. Within decades of that first breakthrough, commercial warp drives might ferry passengers between Sol and Alpha Centauri regularly. Mining operations could harvest resources from distant solar systems and return them to Earth markets. Scientific expeditions could visit thousands of potentially habitable worlds, cataloguing alien biospheres and searching for evidence of other technological civilizations. Permanent human colonies might establish themselves on the most promising exoplanets, creating new branches of human civilization adapted to their local environments. Some might diverge so dramatically over centuries that they become distinct cultures, or even subspecies, united by common origin, but separated by vast gulfs of space and independent evolution. The galaxy contains approximately 400 billion stars. Hundreds of billions of planets orbit those stars. The numbers become so large they lose meaning to human intuition. But with warp drive technology making interstellar distances traversable, even a tiny fraction of those worlds becomes accessible. Humanity could expand from one planet around one average star to thousands or millions of settlements throughout our galactic neighborhood. Our entire future history, everything our descendants might achieve over coming millennia, depends critically on whether we successfully develop faster than light propulsion. The barriers that confine humanity to our cosmic neighborhood might finally be bending under sustained scientific pressure. The universe that seemed impossibly large and forever out of reach might become genuinely traversable within this century. The stars that appeared permanently beyond human reach might welcome explorers within our lifetimes or our children's lifetimes. Scientists have introduced revolutionary new ways to potentially travel 10 times faster than light, and that singular achievement could fundamentally transform our species from planetary inhabitants into true galactic citizens. The long journey toward breaking physics' ultimate speed limit has genuinely begun in laboratories worldwide. The only remaining question is how long until we finally break free from our cosmic cage and spread throughout the stars that have beckoned humanity since we first gazed upward in wonder. If you enjoyed this exploration of humanity's greatest scientific challenge, don't forget to leave a like and subscribe for more journeys into the profound mysteries of the universe.